This is the second of two lectures on dimensional analysis. As I indicated at the end of the last lecture, the problems to be confronted with are two. First, where qualitatively does the structure of physical quantities come from? What kinds of qualitative properties would lead to that structure that is familiar to us from physics? And secondly, having answered that question, why should one be considering only dimensionally invariant laws? To get some idea of what the problem is in the construction of the structure of physical quantities, let me point out one well-known fact, but it is a fact that requires some explanation. Suppose I have a conjoint structure in which the attribute that I am measuring is momentum, and the factors I am manipulating are mass and velocity. I will then be led to a representation that says that the qualitative momentum is describable as the product of a mass measure times a velocity measure, where I am using mass and velocity in this discussion of the conjoint structure merely as labels to describe stimuli. The measure that I come out with is dependent on the mass on the one hand and dependent on the velocity, but not necessarily the same as the usual mass measure. So what I'm saying is that let me think of the typical element as describable as mass paired with velocity. Then the theory is saying that if these are ordered by momentum, the theory is saying that there's some measure of mass and some measure of velocity that is order preserving. Now, of course, there are, on the individual components, using the fact that there are extensive structures involved, there is the usual mass measure, which I'll just write as m, and the usual velocity measure v. And what's not obvious at all is why this measure, derived from momentum, has any simple relationship other than monotonicity to the mass measure. In fact, in this particular example, in the usual way it's measured, you would say that phi1 of m was simply proportional to m, or actually it would turn out it's proportional to a power of m, and that phi2 of velocity would be proportional to the same power of velocity. Now, it's not at all obvious why that connection exists, and in a sense that is the problem, to try and understand that connection. And in the second part of Chapter 10, there is a discussion of certain types of laws that would lead to that kind of structure. Since that chapter was written, considerable progress has been made on the problem, and I will approach it from this new point of view in this lecture. And that material is drawn mainly from the chapters on non-additive concatenation and the chapter on meaningfulness. What I want to talk about, as was suggested by that example, are triples of structures that involve, on the one hand, a conjoint structure with a first component A, a second component P, an ordering of that conjoint structure, and I'll assume that it's a weak ordering and that independence holds. But I don't assume anything stronger than that. I'm not assuming double cancellation or the Thomson condition. I'm going to admit at this point of the discussion something more general. And I also am going to have closed operations on at least some of either the first component, which I'll denote by O sub A, or the second component, which I'll denote O sub P, or on the Cartesian product, which I'll denote O. In the example I talked of momentum, there would be no operation on the Cartesian product, but on each of the components, the mass component and the velocity component, there is a concatenation operation. I will define for each of these types of operations what is to be meant by it being distributive. In the case of the operation that's on the Cartesian product, one of two conditions is sufficient to call it distributive. Either you can have that if we pick a particular A in the first component, and then we have a P, Q, and R in the second component, such that this equation holds that A coupled with P concatenated with A coupled with Q is the same as A coupled with R. If that property is independent of the choice of A, that is, I can substitute B in here and still have a valid equation, I'll say that O is a distributive operation. Or the other way around, that the common value is on the second component, and I have an A, B, and C that satisfies that equation. I can change the second component to any other value, P prime, everywhere, and still have a valid equation. That's what I'm going to mean by saying the operation O is distributive. When I go to the operation O sub A on the first coordinate, the definition is as follows. Suppose I have a fixed P and Q, which appears in both of these equations, an A and a C that causes an equality, a B and a D that causes an equality. Then the assertion is that keeping the P in this second coordinate here and the Q here, that when I compose the A with the B and the C with the D, I get an equality. And a very similar definition holds for the operation in the second coordinate. This is going to be the concept of distributive operation, and it turns out that under solvability conditions, we might just as well assume we're dealing with an operation on the first coordinate, because each of the others will induce an operation on the first coordinate which is distributive. In particular, if I have the operation on the Cartesian product, I'll first induce an operation on the second coordinate in the following way. I will define, oh dear, I have made a mistake here. What do I want? This is P, little p. I will define for any P and Q the concatenation of them in the second coordinate will be the element R, provided that the equation APO, AQ is indifferent to AR, holds for all A. Now, as we indicated over here, the definition of distributivity is that it does indeed hold for every A, if it holds for any A. So that defines the operation OP that's induced by O, and it can be shown that if O is distributive according to this definition, then OP will be distributive. And similarly, OP induces an operation on the first coordinate in the following way, and here's where solvability is needed. Let me take any pair of elements A and B, and I fix an A0 and a P0, and I essentially map the A term over into the second coordinate, call it R, the B into the second coordinate, call it S, and then define the concatenation of A and B to be the element C that results from solving the equation back in the first coordinate from the composition of R with S in the second coordinate. And again, the distribution property is induced. So we'll, with no loss of generality, just talk about, for the moment, about operations on the first coordinate. So what we're thinking about at this point is a Cartesian product with the beginnings of say, a positive concatenation structure on the first coordinate with a closed operation O sub A. Now I want to describe some of the things that arise from the assumption that an operation is distributive, but before I do that, let me point out one thing. Remember, in our study of general conjoint structures, we induced an operation on the first coordinate that reflected the conjoint structure. That was our technical device, actually, for proving a representation theorem for conjoint structures. We first saw it in the case of additive conjoint structures, and then in the general case. And so we have always that operation, which I call star of A, induced on the first coordinate. And the first theorem is that operation is not distributive. And the proof is very simple. I mean, suppose it were. Look at the equation. Remember, we defined pi of A as the image and the second coordinate of A relative to the fixed points P0 and A0. And just write that equation twice, exactly the same, and then use the distribution property on the assumption that star of A is distributive. Then it says A star of AA with P0 is the same as A0 star A of A with A0 with pi of A on the second coordinate. But we showed that A0 acted like a zero element or an identity element, so that means that this is actually the same as A0 pi of A, and that by definition is A pi of P0. And using independence, then, we conclude that A star A is indifferent to A on the first coordinate to A. However, we know from the previous results that this induced structure on the first component is a positive concatenation structure, and therefore, in a positive concatenation structure, A star sub A joined with A has to be strictly greater than A, contradicting that. Where did we get into trouble? It was on the assumption that this is distributive. Therefore, we conclude that it is not. Now, let's go back to the general problem where we have a new independent operation, O sub A, on the first coordinate that's carrying empirical meaning. And let us suppose the conjoint structure is solvable relative to A0, P0, and that's a minimal element. We'll assume OA is closed, and that the structure on the first component involving OA I'll assume to be a positive concatenation structure. The theorem then says several things. There are three parts to it. The first is that if the conjoint structure satisfies the Thomson condition, in other words, if the conjoint structure is really an additive conjoint structure, and if theta is an automorphism of the positive concatenation structure on the first component, then the operation is distributive if and only if equalities are preserved under the operation of the automorphism. And that's an if and only if statement. But the property of being distributive has a very close tie-in with the automorphisms acting in the first component and how they're related to the conjointness. There's a tie that is being established. Well, obviously, distributivity establishes a tie, and it can be restated in automorphism terms. The second part does not presuppose the Thomson condition. It's not an assumption. It simply presupposes that the structure on the first component, script A, which involves the operation O sub A, we'll assume that that's a fundamental unit structure and that it has a unit representation. Now recall that fundamental unit structures always have unit representations, and that unit representations involve ratio scaling. So we're making an assumption here that we have a ratio scale representation of the positive concatenation structure. And secondly, let's assume that O sub A is a distributive operation. Then the assertion is that there exists a mapping of the second coordinate such that phi of A times psi of P is an order-preserving representation of the Cartesian product. Now notice what's happened here. The conclusion is that the Cartesian product is in fact, or the conjoint structure is in fact an additive one. Just take logarithms and you have the additive representation. I'm sorry, this should be in the positive reals. And we've gotten that not by assuming the Thomson condition or any of the cancellation properties usually involved. All we have assumed is that we have got ratio scaling on that first structure and that it satisfies the distribution property. And those two alone force the representation to be that of additive conjoint measurement. The third part simply adds another closed operation, and I've stated it on the second component, but recall that if there was another distributive operation, let us say on the Cartesian product, it would induce a distributive operation on the second component. So I'm making no real assumption other than that I have two closed distributive operations in the system. And it doesn't matter where they are, they can always be, they always will induce operations on both the first and second components. So I'm now assuming I've got an operation on both components, and I'm also assuming that the induced operation is again a fundamental unit structure, and so it has a unit representation. Then the conclusion is that the conjoint structure is represented by a product of powers of the two unit representations. And that is the classic structure that one has postulated or not postulated, that is the building blocks of the structure of physical quantities. Notice that the representation is, of course, unique only up to an arbitrary positive power, but that the two fundamental units, or the unit representations, come in with different powers. That this constant alpha is a characteristic of the situation, whereas the constant beta is simply a conventional choice of what the exponent will be. And that harks back to what I said about the momentum case, that there was a free exponent here. I wrote it as alpha here, but if I use beta here, it'll be analogous. So we've got the kind of tie-in between fundamental unit structures and their unit representations and the conjoint structure that is commonly found in the physical sciences, namely a product of powers. And of course, in almost all the examples that I know of in the physical sciences, the fundamental unit structures that are in fact used are the special case of extensive structures. But the important thing, as far as the theorem is concerned, is whether you have a ratio scale or not. That in proving the theorem, it is the ratio scale property that plays a crucial role in developing the proof of the structure. I emphasize again that we made no assumption in developing this that the conjoint structure was satisfying the Thomson condition or additive in the first place. That additivity of the conjoint structure is being forced on us by the assumption that we're dealing with a distributive operation and a ratio scale of that structure. For classical physics, then, the assumption of distributive operations being coupled in with conjoint structures seems to give a perfectly adequate account of the trinary relations that one finds in the structure of physical quantities. There are, however, some unusual cases that have to be mentioned and that are, I think, a distinct problem, and the theory needs to be generalized in some fashion to deal with them. Relativistic velocity is the most notable one, and it does not provide, the concatenations of velocities is not a distributive operation in the triple composed of distance, velocity, and time. And you can see this as follows. Suppose that I use the usual length, time, and distance measures. I have the velocity u and the time tau equaling some distance and equaling a different velocity v at a different time t, and similarly u prime tau is equal to v prime t. If, in fact, it were a distributive operation, the concatenation of u with u prime for time tau should be the same as v concatenated with v prime for time t. That's what the distribution property says. But that is not true. The relativistic combining law of velocities is to take the sum of the two velocities and divide them by 1 plus the product of the two velocities divided by the square of the velocity of light. And if I now just carry through the algebra, I can then substitute for u tau vt, for u prime tau v prime t. That gives us that. And I make the same substitution down here, and you see I've got this term down here, so that that quantity is not equal to this without that term in general, unless t happened to be equal to tau. And that means that the distribution property fails for a relativistic velocity. This is the problem of how to encompass relativistic velocity into this structure has not been satisfactorily solved. Now let me turn to the beginnings of some indication of a connection between these ideas and some of the meaningfulness ideas. Let me consider an unrestrictedly solvable conjoint structure in which there is a closed and distributive operation on the first component, and let me assume that that first component is a fundamental unit structure. So it's the same kinds of assumptions that I made in the preceding theorem, except that I have increased the solvability assumption, but not beyond what is typical in the physical sciences. Now suppose circle plus is another closed binary operation on the first component, distinct from the distributive operation O sub A. Then the assertion of the theorem is that circle plus will be distributive if and only if circle plus is structure invariant in the fundamental unit structure on the first component. So, and you recall, structure invariance was in our lecture on meaningfulness was ultimately interpreted as the concept of what is a meaningful relation in a relational structure. So what this theorem is saying is in the context of the kinds of structures that we need from the physical sciences, the addition of another operation in a component is a meaningful operation that is definable in terms of that component if and only if it is distributive. And the corollary that follows from that theorem and the earlier one that I mentioned is that the induced operation from the conjoint structure is not structure invariant in the first component. Now, at first that seems startling, but if you think about it for a minute, it is not so startling, because what it is telling you is that the conjoint structure, which is reflected in this induced operation, is intellectually completely distinct from the structure that is involved in the fundamental unit structure on one of its components. That is, it is not possible to derive the nature of the conjoint structure from knowing the nature of one of its components alone. That's the essence of that corollary, that you've got embodied in this independent pieces of information, namely the conjoint structure and a single component, so that it's not really such a startling result once you understand exactly what it means. All right, we now have the ingredients for taking three scales and interlocking them. And in fact, I will define as a distributive triple anything that consists of a solvable conjoint structure together with at least one of the three operations, O on A cross P, or OA on A, or OP on P, such that first, each operation is distributive. They needn't all exist, but those that exist, at least one exists, and it's distributive. And each operation, together with either the ordering on that set, which is either the given ordering or the induced ordering on the first or the second component, or alternatively, the converse of that ordering, forms an extensive structure with a homomorphism onto the reals, positive reals. Now, I've added on a couple of things here, and I better be quite explicit about them. The assumption at this point is going to be that we're dealing with an extensive structure, not a fundamental unit structure. The reason being that the construction that we're about to give has been carried out for extensive structures. It has not yet been really generalized to the fundamental or to the unit structure version. I suspect it can be, but that hasn't actually been carried out. The other thing that's a little different is we're admitting the possibility that it won't be the induced ordering, but it'll be the converse of it that enters into the conjoint, into the extensive structure. And the reason for this is that you can certainly have laws that take the general form z equals x y to the minus 2, let us say, in which case the induced ordering from the conjoint structure is the converse of the ordering that's involved in the y dimension, because it's coming in with the negative exponent. And we want to be able to admit that possibility. So we introduce it in that form. Now, that handles three interrelated measures, but as we know, the structure of physical quantities involves vastly more than three, and so some way or another, what we now have to do is piece together a very large number of these distributive triples. And the fact of physics is that one can, in fact, piece them together in a fully consistent fashion. And what I will do is describe a set of assumptions that appear to be plausible and that are sufficient to cause the kind of interlock that we need. So I will present here a model of physical attributes. There's one version of it in Chapter 10, and this is a somewhat improved version that appears in the meaningfulness chapter. We will suppose that there are little u simple orders on different sets A sub I, and these we'll call physical attributes. And you're to think of them as the primitive dimensions for which there is an ordering by the attribute. I'm assuming simple orders here rather than weak orders in order to bypass the problems of reducibility that you have to take care of the equivalence classes that are involved one way or another, and the easiest thing to do is just to postulate that we're working with simple orders to begin with. The second assumption is that for some of these attributes, and we'll choose to label them to be the first T of them, there are operations such that the operation on that set of entities and the ordering or its converse constitutes an extensive structure. So we've got T extensive structures out of the U sets of physical attributes. And third, the third property now tells how the tying together occurs. Let capital U denote the set of the first U integers. We'll assume that there is a set C that is a subset of U cross U cross U, that is U cubed. It's a set of triples that has the following properties. First, if I, J, and K are a triple in C, then the set AK is the Cartesian product of AI with AJ, and the corresponding structures will form a distributive triple. So that the first thing you're saying about the triples that are in the set C is that they are singling out the Cartesian products where the last entry is the product space and it's a product of the first two components. The second assumption is that if you have two triples that involve the same Cartesian product, the same set same attribute, the kth attribute, then they do not have different decompositions. There's a unique decomposition into as a conjoint structure. There's only one that involves this kth attribute. We can say that the decomposition is unique. The third property is going to take a little explaining, but let's see if we can go through it. Suppose K is one of the integers corresponding to a physical attribute, and it is the case that it is not decomposable. That is, for all I and J in U, I, J, K is not in C. That means that it does not have a decomposition as a conjoint structure. Then there are two possibilities that are being asserted. Either that structure, that indecomposable structure, is extensive itself, or there exist extensive structures, two of them, such that K is a component of a Cartesian product, both terms of which are extensive. So you have, in this picture, you have AJ is equal to AK cross AI, or no, it's the other way around, but it doesn't matter, AI cross AK. This attribute is indecomposable, and the assertion is that it's in a conjoint structure where this one is extensive and the composition is extensive. The gist of the requirement here of number 3 is that we're always going to be able, in the case of an indecomposable structure, to express it as an extensive in terms of extensive structures, or itself is extensive. Now, given that the attributes satisfy this model of physical attributes, and incidentally, this seems, from what one can tell looking at the structure of physical attributes, these seem to be an adequate description of that situation. Now, given that definition of the model, I want to define what I'll call a C basis. That is, it's a basis, a concept of a basis set of structures relative to this particular set C that is describing how things interlock. And that is going to consist entirely of extensive structures. So I'm going to insist that the basis be extensive structures, and of one of two characters, either the indecomposable ones, which are the ones that are first mentioned here in 3, or they are the extensive structures that are in a triple, one of whose component is not extensive and also is not decomposable. So that you're in the second part of 3 here, where you're dealing with a structure that's not decomposable, it's not extensive, and that forces these structures to be included among the structures in the basis. What we're trying to get at through this definition is that we're going to be able to reduce all of the numerical structure that we're going to be defining into products of powers of these basis elements. And all of the basis elements are going to be extensive structures, and everything else is going to be definable in terms of them. Now, with that as our definition of the basis, we're ready to state the theorem that answers the two questions that we originally posed. This theorem is number 7 in the chapter on meaningfulness. So our supposition is that we have a relational structure, script A, that consists of all of the sets of elements, all U of them, and U, incidentally, is a very large number in this situation in practice. There are incredible numbers of physical dimensions. The orderings, simple orderings of the U sets, the T operations on the first T of them, and the set C that describes their interrelations. And we'll suppose it satisfies those assumptions that we've just described, and that there is a C basis of extensive structures that I will take to be the first M of the structures. So the notation, the indexing is such that the first M are in the basis, and then from M to T are extensive structures not in the basis, and beyond T, from T to U, are non-extensive structures. That is, they have no operation on them, but they will, of course, by the assumption of the property of C, be involved in conjoint structures with extensive structures. So that's the qualitative relational system that we're going to suppose in this theorem. The relational structure, numerical relational structure, will be the one that I gave earlier as an example. You recall that it involved, as the basic set of objects was the real numbers cross the rational numbers in M copies, where M now is this same M as in the C basis. And of course, this set has we have ordinary greater than or equal to of numbers. We have plus of numbers. We have the star operation. You recall the definition of that was you took the M plus 1 triple tau as a real, and then you have rationals row 1, row 2, row M, and that stars with tau prime, row 1 prime, row 2 prime, row M prime, and that is equal to tau times tau prime, row 1 plus row 1 prime, on up to row M plus row M prime. That was how the star operation was defined. And then we picked out a set of basis elements, and you recall the typical Q sum I consisted of the set composing of tau, and then zeros, except in the ith entry, or 1, and the tau ran over all the possible reals. So that the basis elements in the intended representation involve having the entries, the row entries, all 0 except in the ith position where we have a 1. And this can easily be shown, I think I mentioned before, can be shown to satisfy the axioms of a structure of physical quantities. Now, it's not the most general structure of physical quantities. There may very well, and indeed are, other structures than this that satisfy those axioms, but this is an example of one that does, and it is extremely closely related to the vectorial representations actually used in physics. So we now have the qualitative relational system and the numerical relational system. And the theorem asserts that under the assumptions of that model of physical attributes, there exists a mapping phi from ai into the relational structure that has the following properties. Phi runs over, I shouldn't say where I runs from 1 to u. Now, what properties it has depends on whether it's in the first m, whether I runs from 1 to m, in which case it's corresponding to the basis elements, whether it runs from m to t, which are extensive structures not in the basis, or it's beyond t. And so there are 3 parts telling you what happens in each case. For the ones that correspond to the basis elements, they map it into the basis elements, this structure, with greater than or equal to and plus, and that defines a mapping into the basis elements of the representational relational structure. For the remaining extensive structures, there's a mapping, a homomorphism of the AI into the relational structure, with the OIs being represented as plus. And for the remainder of the non-extensive structures, the homomorphism simply takes the ordered structures into a single dimension of the representation of space script R. And finally, fourth, if I look at any triple of indices that are in C, that is, they're connected as a conjoint structure, then there exists unique exponents row and row prime not equal to 0, and they're actually rational, such that the scale, the homomorphism of the kth dimension, which the kth dimension, of course, being now factorial, when operating on a value ai from the first of the coordinates, the ith coordinates, and aj from the jth coordinate, is expressible as a product of powers of the homomorphism for the ith and for the jth coordinates, with the exponents rho and rho prime. So that this establishes that under the assumptions that we have in the model of physical attributes, there is a homomorphic mapping into this relational structure, which satisfies Whitney's axioms of the structure of physical quantities, and such that the attributes that are in a conjoint structure together, their homomorphisms are related as a product of powers. Moreover, any two homomorphisms are related by a similarity transformation. You recall we defined what we meant by a similarity in the structure of physical quantities, and what we're saying here is that the uniqueness property, that is the partial endomorphism, or actually the automorphisms in the representational structure, that map one homomorphism into the other are, in fact, what the physicists have called similarities of the representational structure. Now, this is very nice because this puts us into the framework that we discussed under the topic of meaningfulness. This is exactly the framework we had there of a homomorphism from one relational system into another, and it means then we can discuss the meaningfulness of relations in that structure, where by meaningfulness, since actually the compatibility requirement is satisfied, then that means that the notions of reference invariant and structure invariant, both in the qualitative structure and in its numerical representation, all three of those notions are the same, and we argued that that really was a sensible concept of meaningfulness. And so what we now have then is a corollary, and this is the answer really to the issue of why physical laws are dimensionally invariant. The corollary says that a relation T in the representation space script R is dimensionally invariant if and only if it is reference invariant in a reference invariant relative to script R. And so by that theorem that we discussed in the lecture on meaningfulness, it is structure invariant in R, and it induces a structure invariant relation in A. Moreover, if I begin with a structure invariant relation in A, there corresponds under the homomorphism from script A to script R, there corresponds a dimensionally invariant relation that reflects in the script R the structure invariant relation in script A. And it's this corollary then that answers the question of why it is reasonable for the physicists to be dealing with dimensionally invariant laws. They are exactly the relations, they define exactly the relations in the representation that correspond to reference invariant and therefore structure invariant relations in the qualitative structure. And if that is a suitable definition of meaningfulness, then these are the class of laws that deal with meaningful relations. And that seems like a satisfactory answer to the question of why we use dimensionally invariant laws in the physical sciences. There remain problems. This is an area I think that is not to be considered finished at this point. We would like to understand more fully what happens when, instead of working with extensive structures, we work with fundamental unit structures. And especially we would like to understand how it is possible to incorporate such concepts as velocity, relativistic velocity, into this network. There seems, in fact, in physics, very little difficulty in incorporating it, and yet, as I pointed out, the operation, the concatenation operation of velocity is not distributive, whereas the arguments leading to this theorem and its corollary that seem to, in a certain sense, solve the questions about dimensional analysis, these all rest on working with distributive operations. And so the theory is incomplete relative to such concepts as relativistic velocity and, I suspect, other concepts of modern physics. So there remains work to be done.